In this lesson, we'll be talking about the angle sum and difference identities. So a common misconception is that the sine, for instance, of a plus b is equal to the sine of a plus the sine of b, like a distributive property. And that's not so. That's why we put a not equal sign there. And let's actually just demonstrate that that's not true. So, for instance, in example 1a, if I wanted to find the sine of 60 degrees plus 30 degrees, the parentheses would tell us that we need to do the 60 degrees plus the 30 degrees first, and then we get sine of 90 degrees, and sine of 90 degrees is equal to 1. Then we can also evaluate the expression sine of 60 degrees plus the sine of 30 degrees. And the sine of 60 degrees is the square root of 3 over 2, and the sine of 30 degrees is 1/2. Whatever that equals, if we combine those two together as the square root of 3 plus 1 over 2, since we have a common denominator, that's definitely just not 1, right? So they're not equal. And let's do the same thing with the with b, different example. This time we're using a cosine function. So cosine of 90 degrees plus 30 degrees is equal to, order of operations would tell us to add first, do the parentheses operation, and then take the cosine of 120 degrees. Remember, 120 is a second quadrant angle, and so when we take its cosine, it's going to be negative. You get a negative 1/2. Now let's find the cosine of 90 degrees plus the cosine of 30 degrees. And the cosine of 90 is 0, and the cosine of 30 degrees is the square root of 3 over 2. So that equals the square root of 3 over 2. In both cases, we can see that the two expressions that we got for each of these answers are not the same. So cosine and sine do not distribute to an angle sum. All right, that brings us to what the actual formula is for an angle sum. And the first angle sum formula that we have is for sine of a plus b. Sine of a plus b is sine a cosine b plus cosine a sine b. There's a plus or minus notation in this formula the way that it's written, and what that means is if you have a plus in between the a and b, there'll be a plus in between the terms on the other side of the equation. If you have a minus in between the a and b, then there'll be a minus on the other side of the equation. There's a similar formula for cosine. Cosine of a plus b is equal to cosine a cosine b minus sine a sine b. And cosine of a minus b is equal to cosine a cosine b plus sine a sinus sine b. Notice the difference in notation. In between the two terms on the right side of this equation, we have minus or plus, which means that the minus on the right goes with the plus on the left. All right, so let's put these to use. We actually have done this one before. We did cosine of 90 plus 30, and we did it by adding the 90 and 30 first and then evaluating the cosine of 120. But let's actually use the angle sum formula this time to evaluate it. So cosine of 90 plus 30 is like saying cosine of a plus b, and that's cosine of a cosine of b minus the sine of a sine of b, where a is 90 degrees and b is 30 degrees. Now we just have to evaluate each one of these individual expressions. Cosine of 90 degrees is 0. Cosine of 30 degrees is the square root of 3 over 2. Sine of 90 degrees is 1. And sine of 30 degrees is 1/2. And so we get 0 minus 1/2, which is negative 1/2. And that's the same result that we got before when we just followed order of operations and we added the 90 and 30 and evaluated the cosine of 120. So this is just to demonstrate that this formula actually gives us a valid answer. I would probably not actually work this example this way if I were given a choice. It's easier just to add the 90 and 30 and then evaluate the cosine of 120. All right, and in B, we have a similar expression. We have sine of 180 minus 45. So let's evaluate that using the sine of the angle difference formula. Sine of A minus B is sine A cosine, oops, I need to put my A in there. A is 180, right? So sine of A cosine of B minus cosine of A sine of B. And now let's just evaluate each of these expressions. Sine of 180 is 0. Cosine of 45 is 1 over root 2, or square root of 2 over 2 if you want to give the rationalized form. And then cosine of 180 is negative 1, because remember 180 is on the left side, and our adjacent side is negative on the left side of the of that circular drawing that we usually make to evaluate trig functions. Finally, sine of 45 degrees is 1 over root 2. And now let's evaluate 0 times 1 over root 2 is 0. Now we have minus a negative, so plus 1 over root 2 is 1 over root 2, or if you prefer the rationalized form of that, square root of 2 over 2. Using order of operations, the other way we can evaluate this is do the subtraction first. We get sine of 135, and that's also 1 over root 2 or square root of 2 over 2, since sine is positive in the second quadrant. All right, in example 3, we're going to utilize these identities to rewrite each of these expressions as a single trig function. So it looks more complicated than it is. All you have to do right here is recognize that this is in the form cosine A cosine B plus sine A sine B, and our identity would tell us that that's equal to the cosine of A minus B. So since our A is 70 and our B is 20, this is the cosine of 70 minus 20, or the cosine of 50 degrees. Now, that's an expression that we can't evaluate any further without a calculator, and so we're not going to evaluate that. It just simply asks us to rewrite it as a single trigonometric function. All right, let's do a similar thing with B. B is in the form sine A cosine B plus cosine A sine B, and that's our formula for the sine of A plus B. So that's going to be the sine of 20 degrees plus 5 degrees, or the sine of 25 degrees. In C, we have an expression that's in the form cosine of A cosine of B minus sine A sine B, and that's a cosine of A plus B. So A would be 130 and B would be 10. So that's going to give us cosine of 140 degrees as a single trig expression. Last one is a sine A cosine B plus cosine A sine B, and that's the formula for sine of A plus B. So that's going to be a sine of A, 54, plus B, 3, or sine of 57 degrees. All right, moving on, we're going to utilize those identities to find a sum identity for the tangent function. So to find the sum identity for the tangent function, we're just simply going to re-express the tangent of a plus b as the sine of a plus b over the cosine of a plus b. Now we're going to utilize the angle sum formulas for sine and for cosine. Sine's formula is sine A cosine B plus cosine A sine B over, and now we have cosine's angle sum formula, which is cosine A cosine B minus sine A sine B. Now that looks like a mess. What we're going to do now is one of those derivation pulling a rabbit out of a hat moves, which is we're going to multiply the top and the bottom of this fraction by 1 over cosine A cosine B. Kind of like simplifying a complex fraction, only we're actually introducing a fraction here. And you'll see why this makes sense. What we're going to do next is we're going to take this fraction here and we're going to distribute it to each of the terms. So if we distribute to the first term, what you'll notice is that the cosine, sine A and cosine A, they're not going to cancel, but our cosine B's are going to cancel. And what that's going to leave us with is sine of A over cosine of A. Then let's distribute to the second term. And here, our cosine A's are going to cancel. What we're left with is sine B over cosine B. And we have a plus sign in between those two after we distribute. Now let's distribute to our denominator. So we're going to distribute the cosine A cosine B, or rather 1 over cosine A cosine B to cosine A cosine B, the first term. And when we do so, everything cancels, and that just leaves us with 1, right? Because cosine A cosine B over cosine A cosine B is 1. Bring down that minus, and then what you'll notice is when we distribute to the second term, nothing cancels. That leaves us with sine A sine B over cosine A cosine B. And now you might be saying, aha, I see where this is going. Each of these terms represents a tangent. So for instance, our first term here, which is sine A over cosine A in the numerator, that's just tangent A. And then our second term, sine B over cosine B, is just tangent B. And then downstairs, 1 minus, and we have part of that fraction, sine A over cosine A. That's just tangent A. And then it's multiplied by sine B over cosine B, which is tangent B. Now, we just did this for the angle sum formula, but the derivation for an angle difference is very similar. So what this gives us is the angle sum and difference identities for the tangent, which are tangent of A plus B is tangent A plus tangent B over 1 minus tangent A tangent B. That's the one that we just derived. And then we simply switch the signs for the angle difference identity. Tangent of A minus B is tangent A minus tangent B over 1 plus tangent A tangent B. Now, a quick word about the angle sum and difference formulas that we just derived for sine, cosine, and for tangent. You do not have to memorize those. Those will be provided for you on the test. All right, let's look at a quick example. All we need to be able to do in this example is to utilize these formulas. We're not worried about memorizing them. So this gives us a description of some angles. Angle A is an angle between 90 and 180, and the sine of angle A is 4/5. That means that we can sketch this angle. That would be a quadrant 2 angle. So quick sketch of that. We're going to have angle A and our reference angle inside the triangle. Sine is 4/5, opposite over hypotenuse. Our missing side is 3, but it's going to be negative because we're in the second quadrant and the adjacent side, or the first coordinate, horizontal coordinate, will be negative. Let's make a sketch of our second angle. This is between 180 and 270, so that's going to be a quadrant 3 picture. And the tangent of angle B is 7/24. So here's angle B. There's our reference angle. The tangent is opposite over adjacent. However, we're in the third quadrant, right? So both of these have to be negative, which is going to give us a positive value for tangent since it's opposite over adjacent. Now we need to fill in our missing side, which is 25, 7, 24, 25 triple. And now let's use those drawings to find cosine of A minus B. Well, cosine of A minus B is just cosine A, cosine B, minus sine A, sine B. All right, let's take a look at our A drawing, and let's fill in the A values. Cosine of angle A is adjacent over hypotenuse, -3/5. Sine of angle A is opposite over hypotenuse, or 4/5. Now let's look at our diagram for angle B. Cosine of angle B is -24 25ths, and sine of angle B is -7 25ths. Right now we just simply have to perform the arithmetic. So we've got 3 times 24 on the top, or -3 times -24 is +72. Downstairs, 125 minus, and then we have a -28 over 125. And so that's going to give us, let's see, what does that add up to? That's giving us 100, right, over 125. Did I do that right? I think so. And then that's going to reduce to 4/5. My apologies. I actually wrote something wrong here. The angle difference formula for cosine A minus B is cosine A cosine B plus sine A sine B. So that's going to change this to a plus. We have plus and negative. Let's change this final answer here. And that's going to be 72 minus 28. And that's going to be 44 over 125. All right, now let's try tangent of A plus B. So tangent of A plus B is tangent A plus tangent B over 1 minus tangent A tangent B. Tangent of angle A is opposite over adjacent, so that's 4 over -3, plus tangent of angle B is, that was given to us, 7 24ths. Downstairs we have 1 minus -4/3 times 7 24ths. All right, let's clean that up just a little bit. Oops, lost my fraction bar. All right, so I'm not going to actually do this addition here, although we could. Wonder if it might be useful for us to do that. Let's just do this without doing the addition. -4/3 plus 7/24 over 1. I'm just going to write this as plus 28 over 72, just multiplying the fractions together. And you remember the technique for multiplying top and bottom by the LCD of all the little mini fractions. That's our best way to simplify a complex fraction. And so we'll get, when we multiply 72 times -4/3, that's -4 times 24, and that's going to give us -96 plus, and then distributing to the 7/24, we'll get 7 times 3, which is 21. Downstairs, 72 plus 28 when we distribute to each term, and that's going to give us -96 plus 21, which is -75, and then downstairs 100, that's giving us -3/4. All right, continuing, we're going to do a few proofs. Some of you might like to start it this way. You need to write down the side that you're working on. Now you can do that, and then you can write on the right side a simplification of that or a re-expression of it. But if you like, you can also start by just writing that side is equal to itself, which is an obvious step, right? That has to be true. Then you can just simply work on the right-hand side and re-express it until it looks like what the right-hand side of the identity is supposed to look like. Well, since we have an angle sum here, we could rewrite using the angle sum identity. So we could rewrite it as tangent of A plus tangent of B over 1 minus tangent of A tangent of B. And what's left to do now is to re-express the value for tangent 45. Tangent 45 is a value that we should know. For 45 degrees, the opposite and adjacent are exactly the same size. That means that the tangent opposite over adjacent is equal to 1. Downstairs, 1 minus 1 times the tangent of theta. And that's pretty much what we're looking for. 1 plus tangent theta over 1 minus tangent theta. And then I'm just going to bring down the left side of the identity on the left side of this equation. And we've now proven the identity, and some folks like to write QED when they're done. All right, in the next we have an angle difference identity. And we can rewrite that. Oops. We can rewrite that, except for we don't have a difference identity for cosecant. So we're going to have to take and write this cosecant of theta as a 1 over sine, since we have an identity for sine. So let's start with cosecant of 90 minus theta equals cosecant of 90 minus theta. And then let's transform the right side. Cosecant is 1 over sine. And then we can use the angle difference identity for sine. Sine of A minus B is sine of A. Cosine of B minus cosine of A, sine of B. Now, since we have a 90-degree angle, we can evaluate the trig functions for 90 degrees. Sine of 90 is 1. Cosine of 90 is 0. And now if we multiply 0 times sine theta, that's going to be 0. So we'll just be left with 1 over 1 times cosine theta, or 1 over cosine theta, which is secant of theta. And then I'm just going to bring down the left side of the equation to show that we've proven the identity. All right. Your turn to try C. So why don't you pause the video and try this one on your own. All right, here's my proof. I used the unrationalized version of cosine and sine of 315 because I saw that the target, that is the thing that we're trying to make this look like, had a square root of 2 in the denominator. All right, here's another one for you to try, D. Pause the video while you work on this one. All right, here's my proof for this one. I just used an angle difference identity and then simplified it using the values for cosine and sine of 90. All right, now let's take a look at a couple other examples. This one looks tricky. Tangent of 2 theta is equal to 2 tangent of theta over 1 minus tangent squared of theta. So let's, even though the other side looks more complicated, I think it'd be best for us to work on the side that is the tangent of 2 theta. So tangent of 2 theta can actually be written as tangent of theta plus theta, right? Because x plus x is 2x, theta plus theta is 2 times theta. So now we can use an angle sum identity to rewrite this as tangent of theta plus tangent of theta over 1 minus tangent of theta times tangent of theta. It's just that theta is both a and b in the identity. Now, when we add two things that are the same together, it's like multiplying that thing by 2, so that's 2 times tangent theta. And when we multiply two like things, that's the same thing as squaring them, so that's going to be tangent squared of theta in the denominator. Now I'll just bring down my tangent of 2 theta, and we've shown that tangent of 2 theta equals 2 times tangent theta over 1 minus tangent squared of theta. That's actually called a double angle identity, and that's something that we're going to utilize in the next section. All right, this next one also has a little bit of a trick involved with it. We're going to do sine of negative theta equals negative sine of theta. So I'm going to start by using sine of negative theta and then re-expressing that right side. Sine of negative theta can be written as sine of 0 degrees minus theta, right? Because if I take 0 and I subtract theta, I get negative theta. Now we have an angle difference, so we can use the angle difference identity, sine A cosine B minus cosine A sine B, and sine of 0 is 0, cosine of 0 is 1, so we have 0 times cosine theta, which is 0, minus sine of theta, which is negative sine of theta. So that shows that if we take the sine of a negative angle, we're going to get the opposite of the sine of the positive angle. All right, here's one for you to try, sine of the double angle 2 theta. So pause the video and try this one on your own. Here's my proof. And we can do this one similar to the one with a double angle that we tried before. The only thing we need to make sure that we recognize is that when we do sine of A cosine of B and both A and B are theta, that sine times cosine and cosine times sine are the same thing. So we can add them together and get 2 times sine of theta cosine of theta. All right, I think there's one more for you to try. Try this next one, secant of 90 degrees minus theta equals secant theta. Pause the video while you try this one. Here's my proof. So I just re-expressed secant as 1 over cosine, and then used the angle difference formula for cosine, found the cosine and sine of 90 degrees, and simplified. We get cosecant of theta. And that's it for this lesson.